So I found a very nice problem in the very first chapter of this nice book on formal languages. I cannot pronounce the author's name, but it's a nice book, and the first chapter has a really kind of beautiful problem. It's pretty simple to kind of follow along with, and I think it's a good example of what a generative grammar is and kind of what it represents. So the first thing the problem states is that you have this language, right? L, which is just what we name our language. And it's essentially, it consists of all of the strings, which is just a sequence of symbols, right? All of the strings that consist of A repeated, because like A concatenated with A, it's like A squared, right? So you use exponentation to kind of denote that. So A repeated n squared times, where n is any natural number. That forms a word in our language, L. So, for example, A itself is just n equals 1, right? A to the 1 is just going to be A the one time. And this would also cover A, right? Because then we just have n equals 2, A to the 4 is 4A's. We wouldn't have A, for example. That would not be cool because there's no n we can pick that will let us do that, right? It's not very happy. So it says, all right, you have this nice language. It's just A repeated n squared times for some n that's 1 or greater. And I'm going to give you a generating grammar that will generate each and every single one of these sequences of A's, right? So the generator is a four tuple, which is just a way mathematicians like to describe four things. And the first thing it consists of is this set of non-terminals. So a non-terminal, it can't end up in the final string, right? And we denote them as capital letters because it's clear, but this is just lowercase a, right? So what we want is everything to just end up as lowercase a. So as long as these symbols remain in our string, you have to keep applying these rules to get rid of them. And if you can't get rid of them, then it's not a valid string, right? It has non-terminals in them. It can't terminate, right, and finish. So we have our terminals, and then our terminal is just A. That's the only finishing sequence. We want our words to just consist of it. Right? And then we have a starting symbol or state S, and it's from the non-terminals, right? So we don't just end as soon as we begin. And we have a system of rules called F, right? So F consists of the following rules. So first, to get away from the start, we have S can go directly towards our little a, right? And that kind of is our first case, right? Or it can go, and a bit more interestingly, to C followed by D, right? These two non-terminals here. And you might be asking, well, we don't have any rules for CD, and I can now give you some for C at least. So C can go to ACB, which is, that's kind of interesting. C shows up in C. This could kind of give you a loop, right? You keep giving yourself more of these A's and B's. And, to kind of give you a way out of the loop, they give you C goes to A, B. And already you might be saying, well, hey, this might be useful. C can kind of generate an unlimited string of A's followed by B's. And kind of play that on your head and make sure that makes sense, because then the rest will kind of come together. So we have another rule. Big A, big B goes to little a, and then BA. And we also have these two rules that kind of allow us to scoot the little a to the left, right? So if it's right next to a big A, or if it's right next to a big B, you just kind of put them on the other side, and, it's all good there. So you also have a couple rules with D. So you have AD and BD, and AD goes to D little a, right? Gets rid of our A's, and this gets rid of our B's by changing it to E and A. So in this case, you're keeping the D, right? This just gets rid of all your A's. And in this case, you're getting rid of a B, but you're also getting rid of your D's, so it can't just clean them up like the prior rule. And now we also have the parent BE goes to EA, and E goes to A. All right, so this thing just denotes the end of a set. So this is all of our rules. And now we're going to kind of see the path that this takes. So this guy tells us where we start. So we just have the symbol S. And we're going to keep applying rules until we're at something just composed of A's, with none of these guys. Right? All right, so we can go directly to A. And that gets us our n equals 1 case from earlier. Or we can go to CD. Now we're at CD. We have two options. Either we can just replace it with AB and be done, or we can do AC and keep applying the rule to itself, right? And by repeated application, we can generate something that looks like A to the I, and then a big C, and B to the I, where I is some number, right? And then finally, we can take that one and then cache in this rule here, the C to AB, and what do you get? You get A to the I plus 1, B to the I plus 1. So you can kind of see how these work in tandem. So if we have our CD, then we can apply this logic and immediately jump through that cycle to either A, B, D, or to A to C, B, D, which can go through this C to A, C, B rule, and now we can just write I and I here, right, because of this relation we found. So these two options, and as you'll notice, this is actually in that set, it's just I equals 1, right? So you do all that, well, actually, it's after we convert this to, we get rid of that final B, and we get I plus 1, B, I plus 1, right? And more properly, these two are equivalent with I equals 0, just gets you this here, right? So now we have, just to simplify it, I'm going to take it down and write that we have A to the N and B to the N followed by D, right? That's the form that this is going to end up in, right? N is some number greater, or is some number equal to or greater than 1, right? So now we have this rule, and when we're looking for ways to apply it, I think it might be useful to rewrite this as A to the N minus 1, and just group that A and B together, and also reduce the exponent on B's side. All right, so now we have this, and we can apply our substitution rule. AB goes to ABA, right? Still flanked on either side by those B's. And if you'll see from our kind of scooting rule earlier, we can move this all the way out at any time because you just go one by one by one, right? But in any case, we've generated an A, right? And what do you know? We can actually group these two instead. So let's write it that way, right? We have our B here. Now we group this A, B, take one down from the B side. So this is B minus 2D, right? And we apply a rule again, and we keep going, and we'll get 2 A's this time. We'll get our A and our B, our A, our B, and minus 2D, right? We'll apply our rule from earlier. We'll end up with 2 A's, and we'll end up in the same exact situation where we want to uncork this guy, but we've now moved one over here. So once we finish moving all of these B's down from the exponent across over, right? This A will generate a little a every time. So now we get A n minus 1 A squared B n and A D, right? So we've gone through all the work of of bringing each a through, and as a result, we get n a little a's generated from this process, right? And now we use our scooching rule, right? And we get these a's all the way over here. So we have an minus 1, bn a d. And if you're getting deja vu, that's because this is pretty much the same exact position we had right up here, with the exception of these little a's here, right? So you're going to apply the same rule for each of these a's, right? And you're going to get a to the n each and every single time. So that's n times n a's, right? So you're going to take this a and bring it all the way across all of the b's, and generate each a until it joins its a over here. So you're going to end up with, same number of b's, same number of a's, just now they're together. But in the process of doing all this, you're going to generate a lot more little a's. So you're going to end up with a to the n squared, because for each of these that you move across, you get a to the n, right? And so now you have a to the n squared. And, we're kind of starting to look like what we intended to get, right? Our a to the n squared. But, we're a bit of ways off, because we still have to figure out how to get rid of this. So let's group the a and the d, because that's really the only rule we have left. There's no BA rule, right? So let me weigh down this envelope. All right, we're here, and we group the a and the d. So what does that look like? That looks like an squared bn a to the n minus 1 ad. And what does ad translate to? It translates to dA. So let's go ahead and do that one. What do you know? We end up with the same exact situation. We've just reduced this big A by 1. We bring it back in, and we get an A on this outside. So we can do that n minus 1 more times, and we get our A to the n. And all of our a's have disappeared, right? They don't come out of this exchange. They've been kind of turned into these little a's. So, but you still have your d, and you have b to the n, and a to the n squared. And so now we're looking at a to the n squared, this thing in the middle, and then a to the n. So maybe there's a way to tie it back to this a to the n squared, right? And one thing you might remember from algebra, if you've taken that already, n plus 1 squared equals n squared plus 2n plus 1, right? And when you multiply things that have products, or that have exponents, you add the exponents, right? So maybe we can get a polynomial, and then we can just say n plus 1 squared, right? So let's see what we can do with this b and d. Now, b and d goes to ea, right? So we take a n squared b n minus 1 bd hit n, and we transform it to n squared b to the n minus 1 and e a. I still have e to the term. And once you know it, we get more BE terms. And each of them is going to give us an A, and it's going to keep the E. So we have n minus 1 more terms. So this turns into an n here, and we can kind of factor out this in a manner of speaking. So I'm just running out of space a bit. But essentially, you run through all of those B's, you delete them in exchange for an A. And now we have, this is 2n, if we combine these two terms. And now what happens to E? Just reduces to A. So you get a to the n squared, a to the 1, and a to the n, which, if you add them together, is the same as this term. You factor it to there, and you have a to the n plus 1 squared. So if you wanted a to the n squared, it's kind of confusing because they're both n's, but essentially, for any n, I can give you a path towards it, because if it's n equals 1, then just right off the boat you go s to a, you're done. Or for any of them, you take n minus 1, you kind of plug it into the his whole process, and You get back n minus 1 plus 1 is n, and n squared, so you're done.